Good day, my viewers. Welcome to another edition of our class on mathematical method. In our previous classes, we have been discussing Legendre equations and Legendre polynomials. In the last class, we started looking at Legendre polynomial of first kind. We were able to generate some Legendre polynomial. We also look at some properties of Legendre polynomial of first kind. The basic property that we look at is the generating function. We told ourselves how generating function looks like. We said the generating function of polynomial of first kind Pn is given as 1 divided by square root of 1 minus 2xt plus t squared equals summation p sub n of x to the power n from 0 to infinity. We use the equation on the board to establish some recurrence relations. We also look at one of the very useful properties of Legendre polynomial of first kind, which is the orthogonality property. We told ourselves that orthogonality property is given as integral from minus 1 to 1 Pn of x dx equals 2 divided by 2n plus 1 chronicle delta dmn. And that is where we stop in the last class specifically. Today we shall continue from where we stop. Once again, you are welcome to this class. I am your facilitator, Legendre Polynomial in your dad. So today we shall take some examples based on the Legendre equations, the generative function of Legendre equation, and the orthogonality property. We look at some example to illustrate what we have discussed so far. Let us take some of the examples. Examples. Let's take the first example here. We're asked to show that Pn of 1 equals to 1. How do we show this? Very simple and straightforward. We use our generative function to show that. Solution. Recall. We recall that summation Pn of x t raised to power n from 0 to infinity equals 1 divided by square root of 1 minus 2xt plus t squared. Now observe that the value of x is given here. So we put x equals 1. If you substitute x equals to 1 in the generating function of Legendre polynomial of first kind, we obtain Pn of 1 t raised to power n from 0 to infinity equals 1 divided by, substitute that here, we have 1 minus 2t plus t squared. The denominator can actually be factorized, and apply law of indices. We will have 1 minus t everything squared all raised to power minus half, which gives summation Pn of 1 t raised to power n from 0 to infinity gives 1 minus t raised to power minus 1. So we are going to expand the right hand side now using binomial expansion. And if we use binomial expansion to expand the right hand side, we will generate summation t raised by n from 0 to infinity. Now compare the coefficients of t raised by n. The coefficient of t raised by n at the right hand side is Pn of 1, and the coefficient of t raised by n at the coefficient at the left hand side is Pn of 1, while that one of the right hand side is equals to 1. And that gives what we are asked to show. Now, let's say, before I take the second question, we may be wondering how this one generates to this. Let's quickly, as a rough work, 1 minus t raised by minus 1. Let's start this way. We note that 1 plus x raised by n is 1 plus nx plus n into n minus 1 x squared divided by 2 factorial plus n into n minus 1 n minus 2 divided by 3 factorial s cube. So that translates to 1 minus t raised by minus 1 as 1 plus minus 1 into minus t plus minus 1 minus 2 into minus t squared over 2 factorial plus minus 1 minus 2 minus 3 minus t raised to power 3 divided by 3 factorial. It continues. This also continues. So by the time we simplify further, we are going to generate 1 plus t squared plus t cube. It continues. And in compact form, it gives exactly what we have here. So let's take another question. Let us take another question. Question 2. Prove that Pn of minus x equals minus 1 raised to power n Pn of x, and hence deduce that Pn of minus 1 equals minus 1 raised to power n. We still use our recurrence relation to solve this particular question also. How do we solve this question? Let's start. The first one, solution. We recall again that Pn summation, Pn of x n from 0 to infinity t raised by n equals 1 divided by square root of 1 minus 2xt plus t squared. Now, if you look at the left hand side, the value of x has been given as minus x. So we put x equals to minus x, call this one equation 1, in equation 1. So we have summation Pn of minus 1 t raised by n from 0 to infinity equals 1 divided by square root of 1 plus 2xt plus t squared. Call this one equation 2. So we go back to equation 1. We substitute t equals to minus t. We do that so that our denominator will be the same. Then we can now equate. In equation 1, put t equals to minus t. We have summation n from 0 to infinity Pn of x equals summation Pn of x minus t raised power n equals summation 1 divided by square root of 1 plus 2xt plus t squared. No, there's no solution. Sorry. Equals 1 divided by square root of 1 plus 2xt plus t squared. Call this one equation 2. Now equation 3. We equate 2 and 3 because the right hand side of the two equations are the same. Equate equation 2 and equation 3. So what do we have? We have at the right hand side, the left hand side, summation Pn of minus 1, t raised power n from 0 to infinity. Apply the law of indices here. We will have this one to be summation minus 1 raised power n Pn of x t raised power n from 0 to infinity. Equate the coefficient of t raised power n. This implies that Pn of minus 1 minus 1 raised power n Pn of x. And that is the first part of the problem. The second part now says that we should use the result. That is the essence of this ends. Anytime ends is used in question, that means that use already generated result to show the second one. And how do we do that? Pn of minus x, yeah, equals to that. Now, if you look at the second result, the second question, in the second question, the value of x is given. Let's call this one equation 4. Put x equals 1 in equation 4. What do we have? We have Pn of minus 1 equals minus 1 raised by n Pn of 1. And already we have generated value of Pn of 1. So recall that Pn of minus 1 is same thing as 1. So therefore, Pn of minus 1 is the same thing as minus 1 raised power n, which established the second part of the problem. Let's take another question. So today we are solving as many problems as we can. Question 3. Given that Pn of x is a solution of the Legendre equation. Legendre equation. 1 minus x squared y prime prime minus 2xy prime plus n into n plus 1 y equals 0. Full stop. Show that Roman figure 1. Pn prime of 1 is half n into n plus 1, and the second part Pn prime of minus 1 equals minus 1 raised power n plus 1 n into n plus 1 all divided by 2. So that is the A part of the problem. B, ends. Obtain the values of Pn prime of 1 plus Pn prime of minus 1. Full stop. That is the question. So let's look at the question again. We were given that Pn of x is the solution of the Legendre equation. The first part of the problem, we have to show two things. That if I differentiate the solution, given that x equals to 1, I will have this. If I differentiate the solution, given that x equals to minus 1, I will generate this. And the second part says that we should add the two results together and see what the final answer will be. Let's start this way. Solution. 1 minus x squared y prime prime minus 2xy prime plus n into n plus 1y equals to 0. Call that one equation. I started with this because the solution contains n into bracket n plus 1, the two solutions here. So it will be better for us to use the equation of Legendre directly. And let's see what is going to happen. Now, since Pn of x is a solution of equation 1, comma, we have, what do we have? We obtain 1 minus x squared Pn prime prime of x minus 2x Pn prime of x plus n into n plus 1 Pn of x equals to 0. Call this one equation 2. Now, x equals to 1, okay? In equation 2 now, let's start with the first problem, number 1. In equation 2, put x equals to 1. If I substitute x equals to 1 at this point, I will obtain 0. So that means that the second derivative cancels out. If I substitute x equals to 1 here, I retain this one minus 2p prime of 1. Then I have n into n plus 1p n of 1 minus 2 Pn prime of x equals, plus n into n plus 1 Pn of 1 is equals to 0. And we have obtained Pn of 1 to be 1. So make Pn prime of 1 as subject of formula. So we are going to have Pn prime of 1 equals n into n plus 1 all divided by 2. And that is the first part of the problem. The first part shown. Let's take the second part of the question. For the second part, the Roman figure 2, we go back to equation 2 and substitute x equals to minus 1 at this point for x. So in equation 2, put x equals to minus 1. Then what do we have? Of course, this also becomes 0. This turns positive. So we have 2x Pn prime of minus 1 is plus n into n plus 1 Pn of minus 1 equals to 0. Make Pn prime of minus 1 subject of formula. We obtain, there is no x here. We have substituted already. We have Pn prime of minus 1 equals minus Pn of minus 1 n into n plus 1 divided by 2. Pn of minus 1 has been obtained as minus 1 raised to power n into n plus 1 divided by 2. Now, apply law of indices at this point. We have minus 1 raised to power n plus 1 n into n plus 1 divided by 2, which is the second part of the A of the given problem. Let's now take the B part of the problem. We are to add the first solution and the second solution and generate values for that. How do you obtain that? B part of the problem. We have Pn of 1 prime plus Pn prime of minus 1 equals, I have n into n plus 1 divided by 2 plus minus 1 is for n plus 1, n into n plus 1 divided by 2. Of course, n into n plus 1 divided by 2 is common to the two of them. So we are left with 1 here plus minus 1 is for n plus 1. That is the value. However, we can move on by saying, suppose we put values for n at this point. What will happen? Let's put odd number here. If I put any odd number here, the whole of the exponent becomes an even number. And by so doing, that turns this one to positive. And 1 plus 1 is 2, which will cancel this. If I substitute even number here, this becomes odd. The exponent becomes odd. And minus 1 raised to the power any odd number is negative. 1 minus 1 will give us 0. So that means that we have two major results. The first result is 0 if n is even. And the second result is n into n plus 1 if n is odd. And that is the value as instructed from the question. Let's take another question. Let us solve another question. And that will be question number 4, if I'm not wrong. Question number 4. With the aid of the generating function, comma, establish generating function of Pn of x, comma, establish that Roman figure 1 P2n plus 1 of 0 is 0, and Roman figure 2 that P2n of 0 minus 1 raised to the power n 2n factorial divided by 2 raised to the power 2n n factorial all squared. In the question, we observe two things. Number one, that the Roman figure 1 contains odd subscripts, and Roman figure 2 contains even subscript. And the question instructs that we must use generative function to establish the two results. How do we use generative function to establish the two results? Let's start. Now, let us recall our generating function. Solution. Recall that summation Pn of x, n from 0 to infinity, is the same thing as 1 divided by square root of 1 minus 2xt plus t squared. Now, from what we have, the value of x is given as 0. So put x equals to 0. Call this one equation 1 in equation 1. We have t raised to the power n. We have summation Pn of 0 t raised to the power n, n from 0 to infinity, equals 1 divided by square root of 1 plus t squared. I can write this one as 1 plus t squared raised to the power minus 1, which can be written as raised to the power minus half, which can be written as 1 plus minus half t squared plus minus half minus 3 over 2 t raised to the power t squared squared divided by 2 factorial plus minus half minus 3 divided by 2 minus 5 divided by 2 t squared raised to the power 3 divided by 3 factorial plus it continues. This is a negative plus times minus. The whole of this one is positive. That the sign alternates, and that takes care of minus 1 raised to the power n. It alternates signs. So from here in compact form, let's see what is going on. The first term is since we have seen that the sign alternate, let's take all the positivity. The first term is half there, followed by half 3 over 2. We have half 3 over 2 into 5 over 2. The next one will have been half 3 over 2, 5 over 2, 7 against 2. This will have been half sub 2. That's a factorial function. Half sub 3. And this is half sub 4. Okay? There's a general term already. So, this is interesting. This implies that Pn of 0, n from 0 to infinity, t raised to the power n will have given us summation minus 1 raised to the power n half sub n, n from 0 to infinity, half sub n, then divided by n factorial t raised to the power 2n. Now, the right hand side suggests that all what we have here, they are even power. So what do? We come back to the left hand side. We can divide this one into 2 by saying that I can write this one as summation n equals odd to infinity Pn of 0 t raised to the power n plus summation n equals even to take care of this infinity Pn of 0 t raised to the power n, everything equals summation n from 0 to infinity minus 1 raised to the power n half sub n divided by n factorial t raised to the power 2n. From there, the left hand side can be rewritten. And how do we write that? Since this one is odd, let's use the general term of odd number. We're going to have n equals to 0 to infinity. P2n plus 1, which is the general term for odd, t raised to the power 2n plus 1 plus summation n equals to 0 to infinity for the even P2n of 0 equals t raised to the power 2n. Everything is the same thing as summation minus 1 raised to the power n half sub n divided by n factorial t raised to the power 2n. Now let us compare n from 0 to infinity. By comparison of left hand side and right hand side, we will see that at left hand side there is no coefficient for t raised to the power 2n plus 1. That implies that p 2n plus 1, so Roman figure 1 now, of 0 will automatically become 0. Now for the Roman figure 2, we have the even power. So compare the coefficients here. So we are going to have p 2n of 0 is same thing as minus 1 raised to the power n half sub n divided by n factorial. Now, before I proceed with the question, we will observe from here that the whole of the left hand side can be written in terms of hypergeometric function at this point, this particular point. And how do I mean? That means that the examiner can change the question to show that summation Pn of 0 t raised to the power n from 0 to infinity is the same thing as f. We can introduce factorial function, a arbitrary factorial function. Let that one be k, comma half, semicolon, k, semicolon, minus t squared. That would have been the result if I want to convert it to hypergeometric form. So in essence, mathematics cannot be learned in isolation. So many topics in mathematics are interwoven. As you are working with a particular topic, another one can come in. And as soon as you encounter that one, you just have to apply the necessary rules. Failure to do that, one may not be able to continue. So from this point, I can write the whole of the left hand side in terms of hypergeometric form of the right hand side. And that will have been the result. So let's go back to what the question asked us to do. Let me go back to the question. Where are we going to? The question, we are going to where's the question? Okay, we are going to minus 1 raised to the power n 2n factorial divided by 2 raised to the power 2n n factorial squared. So the major concern is a half sub n, which is a factorial function. So let's continue from there. P2n of 0 minus 1 raised to the power n. This one will have given us half 3 over 2, 5 over 2. It continues until I have half plus n minus 1, all divided by n factorial. That gives minus 1 raised to the power n. At numerator we have 1 times 3 times 5 up to 2n minus 1. At denominator we have 2 in n places, and that gives us 2 raised to the power n. Then I have n factorial. Observe at numerator that what we have is purely odd terms. 1, 3, 5 up to 2n minus 1. So let us insert the missing even terms in between the odd term. How do I mean? Minus 1 raised to the power n 1 multiplied by 2, multiplied by 3, multiplied by 4. It continues. As we are doing that, you are also cancelling at the denominator. That is 2 cancel 2, 4 cancel 4. It continues. Now, the general terms for even is 2n, and what we have there is 2n minus 1. You observe that 2n is greater than this. So that means that in the arrangement, I will write this one as 2n minus 1, then 2n, and lastly 2n. At numerator, we don't have any problem again. What we have at numerator now is 2n factorial, because that's what it defines. Minus 1 raised by n, 2n factorial. A term is missing here. Let me put it this way, n factorial. All divided by 2 raised power n. Observe that each of these even number can be written. For instance, 2 can be written as 2 times 1. 4 can be written as 2 times 2. 6 can be written as 2 times 3. It continues, and we write this one as 2 into n. Then multiply by n factorial. Multiply by n factorial. Then, what does that translate to? What does it translate to? Let us look at the translation. Let's first consider all the outer 2. 2. We say that we have 2 in n places here. That gives minus 1 is by n, 2n factorial divided by 2 raised by n. Then we have another 2 raised by n, 1, 2, 3, up to n, then n factorial. What I have here defines n factorial. And finally, we are going to obtain the desired result.